My name is Grace Fenech, and my partner is Yash Patel, and we had question 7.4 on this homework assignment. From experimental data, it is known that at moderate pressures, the volumetric equation of state may be written as PV equals RT plus B times P, where the second variable coefficient B is a function of temperature only. Data for methane are given by Diamond and Smith, which is the chart given below. For part A, identify the boil temperature and the inversion temperature for gaseous methane. And for part B, plot the data versus 1 over T and compare it to the curve generated from equation 7.7. Use points without lines for the experimental data and lines without points for the theoretical curve.
Okay, so for part A, we are asked to plot B versus 1 over T. And using MATLAB, we get the equation for the curve fitting of negative 2.61 times 10 to the 6th x squared minus 1.71 times 10 to the 4th x plus 44.53. Setting that equal to 0 and solving for T, we can get that T is equal to 504 Kelvin.
To find the inversion temperature, we know that dt over dp with constant h times dp over dh with constant t and dh over dt with constant p equals -1 with the triple product. Simplifying this equation, we get dt over dp with constant h equals negative dh over dp with constant t over dh over dt with constant p. We know that dH over dt with constant p is equal to Cp, and that dH over dp with constant t is equal to T ds over dp with constant t plus V times dp over dp with constant t. We can simplify the dp over dp to 1, and we know that ds over dp with constant t is equal to negative dv over dt with constant p. Simplifying and plugging those values in, we get dt over dp with constant h equals t times dv over dt with constant p minus v over cp.
And using that equation, we want to get dv over dt into something else. So we start with our equation giving in the equation giving us PV equals RT plus B times P. Rearranging and getting P to the other side, giving us V equals RT over P plus B. Then taking the derivative with respect to T, giving us R over P plus dB over dt with constant P. We can also use the equation of state, which says Z equals to 1 plus B over V, knowing that V is equal to RT over P, and substituting that in, then multiplying by RT over P, giving us V is equal to RT over P plus B. Now plugging in everything that we have so far, we can cancel out RT over P, and then we're left with dt over dp with constant h is equal to T times dB over dt with constant P minus B over Cp.
We can rearrange the equation to get dt over dp with constant h is equal to T times B over T minus dp over dt with constant P over Cp is equal to 0. This is the Joule-Thomson equation, and simplifying the equation, we'll set B is equal to T dB over T dt with constant P. From the initial equation in part A, we know the equation for B. We take the derivative of this, multiplied by T to get 5.922 times 10 to the 6th times 1 over T squared plus 1.714 times 10 to the 4th times 1 over T. When we set B equal to T times dP over dt with constant P, we get T is equal to 963 Kelvin.
In part B, we're asked to plot the data from what we just got versus versus what we got in part A. And the dotted points show from what we got from part A, and the solid line is what we got for part B. And oddly enough, they match.